Here is a modified levitating globe desk gadget. As you can see, it is levitating. The way it normally works when you buy it, there is a circuit here, electromagnetic circuit with a sensor that is able to tell how strong, how many sort of like pulses of this electromagnetic field should be created to hold it in place, not allow it to drop, but not sort of like suck it all the way up. So that's how it works. Normally there is sort of like LED lights here. I remove it here. The main weakness of this toy is that normally it does not rotate, and basically when you apply some sort of like rotation with your finger, then obviously it will rotate for 10-15 minutes and then it stops. But I wanted this to rotate continuously without me sort of like having to actuate it. And I modified this. I will explain the circuit in a minute. I modified this. I want to show you how it works. It usually needs some sort of like initial spin. I show you maybe how it works. This is sort of like a little bit of a reflective type tape here. Okay, this allows my circuit to know the globe position, and here in the base there is IR diode and a phototransistor here. So there's phototransistor and diode here that is able to sense the position of this marker of this aluminum foil. Okay, there are some diodes, LEDs here in front to tell me the status. There is a power, green. The yellow tells me if the circuit protection, the thermal protection sort of like kicks in, then this yellow goes off, and here is detection of the marker. So every time the phototransistor detects the marker, this will go red. Okay, let's put this into the place. It does require a little bit of a practice. It needs to be, because otherwise this happens. So it needs to be in its sweet spot. Good. Okay. And now we give it initial kind of rotation, and now we should see that every time it detects the spin, here the red goes on. All right. So every time the marker, here we go, goes above the phototransistor, it detects it. So here you can see the marker is about to go there, and here it is, red. Alright, here it is, the marker, and the marker goes above the phototransistor, and every time the phototransistor goes on, there is an electromagnet here, a little magnet in this part, and it creates enough of electromagnetic power or a magnetic field to spin the globe. The globe itself has asymmetrically positioned some form of magnetic material that responds to the magnetic field, that is sort of like attracting the globe and sort of like making it sort of like go into this more magnetic active part. And as you can see, the globe starts to spin sort of like more and more, and finally it stabilizes at certain speed. Because this electromagnetic coil creates some heat, I did venting holes in the enclosure, so that it runs a little bit cooler. and now it basically spins continuously. It doesn't stop. It spins without any stopping. That was the whole principle. And here it is. The thermal protection kicked in. Electromagnet sort of like is too hot, so the yellow goes off. And right now, as you can see, there is no triggering. Red is off. The globe has enough, obviously, momentum to keep on spinning until the coil cools down, and here it is. And now the circuit is active again, right? And we'll see that the thermal protection will kick on. Here it is, every now and then. I set it to around 60 degrees centigrade. I think it's roughly what it is. And this thermistor that is sensing the temperature of the coil sits literally on top of it. It's sort of like it's sort of like around it. If I make the impulses maybe a tiny bit shorter, then the thermal protection would kick in a little bit less frequently. But it really doesn't bother me. It can spin all day without causing much of a problem and without getting too hot. It will keep the coil itself on this point of 60 degrees and won't allow it to go any higher than that. So that's how it works. I removed the lights because obviously that is I didn't like it in the first place. So that's removed. Another thing that I had to do to make it triggering sort of like better is to put a little bit of a separation between the illuminating diode, illuminating LED, and the phototransistor, because otherwise they were sort of like sensed at exactly the same time. They were basically, the transistor was getting enough light spilled all over from the LED to trigger. But this now works very consistently, very nice. It doesn't like direct light on the transistor, so when I put my desk light on it, it will trigger, and probably in direct sunlight, I can imagine, also could potentially trigger. But otherwise, it does work. It does work quite nicely. The power supply is slightly upgraded, because the original one is only 1 ampere, and this may not quite work well, because each of these coils, the one that keeps the globe levitating, and right now my coil that keeps the globe spinning, probably needs somewhere in the range of at least half an amp, probably a little bit more. So I run it currently from 5 amp power supply, and it is more than enough. Okay, I'll show you the circuit, and as you can see, it keeps on sort of like spinning. It will spin at this rate right now for as long as it's plugged in. I think it's much more attractive than just sort of like globe hanging without this rotation. And you need to sort of like do it with your finger. And when it is quite sensitive, when you do it with your finger, then it quite often you upset it, and it again loses this balance and gets sucked up into this top magnet. So I'll show you the details of the circuit. I hope it will make sense. Yeah, I'm not going to show you the detailed schematics. It is quite simple, so I'm pretty sure you can, and the elements are not critical. I'm pretty sure you can work it out, and it's a little bit of a fun also to build it yourself. So here is the diodes, the phototransistor, and the LED sits here in the base, and then all the electronic PCB is here, and here is the electromagnet. I put a coil here. This is where the where the coil sits. It is a coil from the doorbell, old-fashioned doorbell, that was designed originally to work with 9 volts AC current, but here I'm using DC current, and it is activated. It is synchronized. The magnetic field here that is created by this coil is synchronized with the globe position. You can see here there is a strip of foil, reflective kind of foil, silver foil. It's a normal kitchen aluminium foil. There's a strip here that is attached to the globe, and what it does, it reflects a infrared light. Here is an infrared LED that is illuminating the globe, and here is a phototransistor that detects the light reflected from this strip, and that way it agitates the coil, energizes the coil, and then the globe starts to spin. Here you can see it's still sort of like the experimental it is still experimental design here, so it's not fully packed in, but here you can see every time it detects the strip, the LED goes on, just so I know that it actually creates a magnetic field. It is double trigger because probably one of the continents here is also reflecting a little bit of this light. You can adjust the sensitivity of detection with this potentiometer here. So this still needs a little bit of fine tuning, but it does work. What this circuit here does, because the coil gets quite hot, as I said, the current flowing through this coil heats it up, and I'm not sure if you can see, but there is a little thermistor here. There is a temperature sensor over there, sitting on top of the coil, and here it is, the temperature is detected and compared to my threshold, to what I want it to be, and then if the coil heats too much, then the circuit stops working for a moment. As long as it's within the temperature range, this LED is lit. Oh, here it is. It is now off, so the circuit is off. And now when the temperature drops back to the safe level, the whole circuit starts working again. I set the temperature to 60 degrees centigrade. Here I use this switch to manually trigger the whole circuit, and this is to regulate the width of the pulse, so how long does the magnetic pulse last. This will be replaced by the fixed resistor. This will go, and everything will go inside the globe, inside the enclosure here. There's enough space for it. An electronic circuit is based on the principle of sending the electromagnetic pulses or magnetic field switches on and off, making the globe to rotate, giving basically an impulse. Because normally when you do it with the finger, after 10 or 15 minutes, the globe will stop. The whole thing is the whole principle, the whole idea was to make it spin on its own and maintain the rotation speed. And I've noticed that when you put a magnet close to the globe, it will follow the magnet. So there is some inside some magnetic material that is asymmetrical, and we can attract the globe rotation by putting a magnetic field close to it. And so the idea was to use electromagnet that would sync with the rotations of the globe, and it will make the globe rotate. So I'm going to show you the idea rather than the values. The circuit is very simple, so I'm pretty sure if you know the basics of electronics, you'd be able to put it into your own practice. It was improvised as I was building it, so that's why I may not remember exactly the values of the elements I used, but I'll show you the principle. So if this is the part of the globe, or the continents around it, then what we want here is obviously magnetic field. So I put a coil close to it, and when I started to excite this coil, put a current, DC current through this coil, pulses of DC current of this coil, I've noticed that the globe starts to respond to it and starts to rotate. Obviously there is a protection diode here. So that's the coil. That's the main element that drives the rotation of the globe. Here is ground, and here obviously we need something that will be powerful enough to put a current through this coil. The coil I use, and the coil that fits into the enclosure here, is doorbell coil. It's a normal 9 volts doorbell coil electromagnet. That's at least what I found in my spare parts cupboard. So we need to put this into the MOSFET transistor, because MOSFET transistor should be powerful enough to drive this coil without heating too much, without losing too much of a power on its own. The transistor I use is actually called IRF 520N. But I guess you can use any MOSFET, and power MOSFET here. So that is being driven by good old 555. That is sending 1 second, roughly 1 second. I think right now it is a little bit longer than 1 second, but it is about 1.5 seconds pulses. So here we have basically 1 second pulses, but that it needs to be synced with the globe. If you just send random pulses or irregular pulses, the globe won't spin. 555 needs to be powered, so plus 12 volt. It goes to the minus here, to the ground. We need obviously appropriate values of So that will, this resistor and capacitor combination should give 1 second activations. Now, we know that the 555 responds to the input to the 555 when we activate. It needs to be low. So when the input to the 555 drops below 1/3 of the supply voltage, then the 555 activates. So we need to find a way to activate it with low voltage here. Now, how to sync the globe rotations, how to make sure that the 555 knows when to send a pulse to the coil. There are probably many ways of doing it. I decided to actually use the phototransistors and the IR LEDs that I had in my drawer. But we need to sort of like translate the phototransistor detecting a voltage into nice high, low states. So as you know, phototransistor, the more light goes on it, the more current flows through the phototransistor, which is sort of like continuous from not conducting to full conduction. Whereas we want on-off kind of device that works like a trigger. We could use some Schmidt triggers, but I decided to use here a voltage comparator. So here is our voltage comparator. I use again power plus 12. I use LM339, but really you can again use any voltage comparator. Because LM339 has an open collector circuitry inside, we need to give a pull-up resistor. I think I use something like 4.7 kilo here. Okay, so this voltage comparator is going to translate continuous sort of like detection of the light from the phototransistor into the pulses, into the nicely defined pulses for the 555. So we need to have it has plus and minus, inverting and non-inverting kind of input. To the plus input, I connected a I think it was 20 kilo potentiometer that will allow me to sort of like set the trigger, the sensitivity of the phototransistor triggering. And here to the negative kind of side we connect finally our phototransistor. So here it is. So that's our phototransistor, and obviously it needs a resistor here. Again, I'm not sure what value I use here. Again, I suspect it was 4.7 kilo. These values are not really critical. And then we need something that will this phototransistor in respond to. So we need an LED, and I use a IR diode. I think it was 820 nanometers IR. So this diode, it should also have a current limiting resistor, obviously, to have 20 milliamperes. So what is happening here? This diode is continuously illuminating the globe. and when there is a little aluminium foil on the globe that reflects this light, and that goes on the phototransistor, and there is a peak happening on the phototransistor. When this light is detected, this line goes low, so the LM339, when this is low, it gets activated, so this also goes low, and 555 responds to low voltage on the input, and it's activating the coil. And that's basically principle of that circuit, how it works. I've noticed, however, there was one problem with it. As I said, the coil here is supposed to work with 9 volts, and it was getting very hot when this cycle, when the globe was spinning quicker and quicker, faster and faster, and the impulses were faster and faster. This coil was getting too hot, so I needed to find a protection circuit that would prevent basically coil from thermal damage. So what we going to do here is on the reset pin, so that's the reset pin of 555. Normally it is connected to that's pin number 4. So normally this pin is connected to high, to 12 volts, to basic supply voltage, for the 555 to continuously operate. I wanted this pin to go low, so switch off the activation of the 555 when the temperature on the coil gets too high. So we're going to use again one of the voltage comparators from the LM339, and what we're going to do, we're going to have this switch on to the 339. Okay, here is again pull-up resistor. We always need that, 4.7K. And then we need to set the threshold. So again, A, of course LM339 also needs to be connected to the supply. So when this is when this 12K again, 12K potentiometer will set it's on the non-inverting input of the LM339. This will trigger the sensitivity. Here you decide the temperature at which this LM339 will sort of like will trigger the reset, or will pull the reset pin to the low. And here we need to have a thermistor, so that is actually a resistor, and here we'll have a thermistor. So that's the basically it's a temperature variable resistor, right? So depending on the temperature, and that is literally sitting on the coil. So this is sort of like our sensor for the temperature, right? And here the value of this resistor should be somewhere sort of like half of the resistance, of the maximum resistance of this this thermistor, roughly. I mean, you want the circuit to operate comfortably, right? To be quite sensitive. So I assume that the biggest sensitivity of the thermistor is somewhere in the half of its resistance. Then it's going to respond to the the temperature changes best, and that's basically how it was decided. So that is ground. This is ground here. So obviously the higher the temperature, the lower the resistance, and at some point the resistance is going to be so low that this non-inverting inverting input will be lower than the inverting input. The transistor here in the open collector output will go active, and the reset pin will go low. So that is, again, that's my protection circuit here, thermal protection. Okay, so we have light sensing here. We have voltage comparator to create the trigger impulses. This is the time of impulse, and this is our coil that gives us gives us magnetic field pulse, and this is the thermal protection. I hope it makes sense, or gives you an idea how this works. Yeah. So that's the Levitating Globe modified.